In the previous video, we introduced the definition of a group homomorphism and we gave several examples. In this video, we're going to talk about basic properties satisfied by group homomorphisms, and in the next video, we're going to use some of these properties to give a proof of a classical theorem known as Cayley's theorem. So let's suppose that phi is a homomorphism from a group G to a group H. The first property that we'd like to prove is that phi must map the identity element in G to the identity element in H. And to see why this is true, first of all choose any element x in the group G, and notice that because x is equal to x times the identity, phi of x is equal to phi of x times the identity. But because phi is a homomorphism, phi of x times the identity is equal to phi of x times phi of the identity. And now, just by left multiplying both sides of this equation by phi of x inverse, we conclude that phi of the identity in G must equal the identity in H. So that was the first property. The second property, which we're going to call 1b, is that if phi is a homomorphism, then for any G in G, phi must map the element G inverse to the element phi of G inverse. Now keep in mind that the G inverse in the parentheses on the left is the inverse of the element G in the group G, and that the inverse on the right is the inverse of the element phi of G in the group H. Well, in order to prove this, let's think about what happens when we multiply together phi of G inverse times phi of G, and we want to show that the product of these two quantities is the identity in H. Well, because phi is a homomorphism, phi of G inverse times phi of G is the same as phi of G inverse times G. But that's just phi of the identity element in G, and we already know from part 1a that that's the identity element in H. Well, now we're done because by basic properties of groups, we know that this implies that phi of G inverse is equal to phi of G inverse. Now, as a generalization of property 1b, we also have what I'm calling property 1c here, which says that for any G in G and for any integer n, phi of G to the n is equal to phi of G to the n. Of course, when n is -1, you just recover property 1b from this, but here what I'm saying is that this property is true for any integer n. Well, I'm not going to go through the full details of the proof here, but this is a relatively easy one and maybe you can already see how the proof works. So you need to use the fact that phi is a homomorphism, and technically you also need to use induction on the integer n. That at least will take care of all of the non-negative integers. But then to prove that this is also true for the negative integers, you need to combine that argument with the result of 1b. I'll leave the rest of the details to you, but this one is not too difficult. Property number 2, which comes up all the time, is that if phi is a homomorphism from G to H, then the image of phi is a subgroup of the codomain. The proof of this one is a good exercise, and for it we're going to use the subgroup criteria. So we need to check a few things. First of all, when you're using the subgroup criteria, never forget to first of all check that the set that you're looking at is actually non-empty. Well, in this case, the image of G is definitely non-empty because G itself is non-empty. Any group has at least one element, which is the identity element, and the image of the identity element is an element of the image of G. Therefore, the image of the group G is always non-empty. Next, we want to check that the image of G is closed under multiplication and closed under taking inverses. So first, let's check that it's closed under multiplication. Suppose that we have two elements, h1 and h2, in the image of G. Well, the fact that they're elements of the image of G means that there have to be elements g1 and g2 in G with the properties that phi of g1 is h1 and phi of g2 is h2. Since G itself is a group, it's closed under multiplication, so the product of g1 and g2 is an element of G. And now, if I just think about what happens when I multiply h1 and h2 together, I get that it's equal to phi of g1 times phi of g2, but since phi is a homomorphism, that's equal to phi of g1 times g2, and so that shows that h1, h2 is the image of a point in G, therefore it's an element of the image of this map. That means that the set phi of G is also closed under multiplication. Finally, to show that phi of G is closed under taking inverses, let's suppose that we have an element h in the image of phi, and let's write it as phi of G for some G in G. Well then, since G is a group, G inverse is also in G. And since phi is a homomorphism by property 1b, we have that phi of G inverse is equal to phi of G inverse. But phi of G is h, so the right-hand side here is just h inverse. That shows that phi of G is closed under taking inverses, and it completes the proof that phi of G is a subgroup of the codomain. There are lots of examples where property 2 is useful, but to see a very simple one, consider this example that we saw in the previous video. So there we defined a map phi from the group of integers to itself by the rule that phi of k is n times k, where n was some fixed integer, and we verified that this map is always a homomorphism. Well, by property 2, that implies that the image of this map, which is the collection of all multiples of the integer n, is a subgroup of the codomain, so that nz is a subgroup of z. That's something which would be pretty easy to check directly, but here we have it as an immediate consequence of the work that we did in the previous video together with our property 2. Next we come to property 3, which is also a very important property. What it says is that if phi is a homomorphism from G to H, then if you collect together the collection of all G's in G, which map to the identity element in H, then that set, which is called the kernel of the map phi, is always a subgroup of the group G. In other words, to say this concisely, the kernel of a homomorphism is always a subgroup of the domain. For the proof, we're going to use the subgroup criteria, so first of all, we'd like to show that the kernel of phi is always non-empty. Well, no matter what homomorphism phi you have, there's always going to be at least one element of G which maps to the identity element in H, because we know by property 1b that the identity in G always maps to the identity in H. That means that the identity of G is always an element of the kernel of the homomorphism phi, so that the kernel is always non-empty. To see that the kernel of phi is closed under multiplication, let's suppose that we have two elements G1 and G2 in the kernel of phi, and let's think about what happens when we multiply them together and then apply the map phi. Well, because phi is a homomorphism, phi of the product of G1 and G2 is going to be equal to phi of G1 times phi of G2. But because each of G1 and G2 was assumed to be in the kernel of phi, phi of G1 and phi of G2 are both the identity element. So on the right-hand side here, we get identity times identity, which is just the identity. Well, now we've shown that the product of G1 and G2 maps to the identity under phi, which is exactly the same as saying that G1, G2 is an element of the kernel of phi. That shows that the kernel is closed under multiplication. Finally, to check that the kernel is closed under taking inverses, let's suppose that G is an element of the kernel of phi, and let's think about what the map phi does to the element G inverse of G. Well, by property 1b, phi of G inverse is equal to phi of G inverse. And since G is an element of the kernel of phi, phi of G is the identity in H. Therefore, on the right-hand side here, I have the inverse of the identity element in H, which I know is just equal to the identity element in H. Well, that shows that G inverse maps under phi to the identity element in H, which means that G inverse is an element of the kernel, and which verifies the claim that the kernel of phi is closed under taking inverses. Now that we know that the kernel is a non-empty subset of G which is closed under multiplication and taking inverses, by the subgroup criteria we conclude that it is in fact a subgroup of G, therefore completing the proof of property 3. We're going to use property 3 a lot in what follows, but just to give a simple example here at the outset, let's look back at one of the examples from our previous video. So there we said that the determinant map from the group of 2x2 real invertible matrices under multiplication to the group of non-zero real numbers under multiplication is a homomorphism. And now let's ask what the kernel of this homomorphism is. By definition, the kernel is the set of everything in the domain which maps to the identity element in the codomain. And in this case, because H is the collection of non-zero real numbers under multiplication, the identity element is the real number 1. So the kernel here is just the set of 2x2 invertible matrices with determinant equal to 1. Now, in case we haven't mentioned this before, this is a special collection of matrices, which we denote by SL2R, and which is called the special linear group of 2x2 real matrices. Property number 3 that we just proved guarantees that SL2R is a subgroup of the group G. The final property that I want to mention in this video is that if your homomorphism phi from G to H happens to be an isomorphism, then its inverse function, phi inverse from H to G, which we know is well defined since phi is bijective, is also an isomorphism. Now, in order to prove this, first of all, let's observe that anytime you have a bijective function phi from G to H, the inverse function is always going to be a bijection from H to G. So that means that we can just focus on showing that the inverse function is a homomorphism. Since it's already bijective, once we establish that it's a homomorphism, that's going to imply right away that it's an isomorphism. Okay, well, in order to do that, let's suppose that we have two elements, h1 and h2 in H, and that the inverse function maps h1 to g1 and h2 to g2. Well, by the definition of inverse function, that's just another way of saying that phi of g1 is h1 and phi of g2 is h2. Now what we're aiming to show is that phi inverse of h1 h2 is equal to phi inverse of h1 times phi inverse of h2. So in order to do that, first of all, let's write the product h1 h2 as phi of g1 times phi of g2. Since phi is a homomorphism, phi of g1 times phi of g2 is equal to phi of g1 times g2. And now, again, by the definition of inverse function, that implies that the inverse of h1 h2 is equal to g1 g2. But remember that g1 is equal to phi inverse of h1, and g2 is equal to phi inverse of h2. So the right-hand side here is the same as phi inverse h1 times phi inverse h2. Well, now that's exactly what I was trying to show, and it finishes the proof that anytime you have an isomorphism from G to H, the inverse function is an isomorphism back from H to G. Finally, for a simple example of this final property, let's consider the map phi from the group of real numbers under addition to the group of positive real numbers under multiplication, defined by phi of x equals e to the x. This was one of our first examples in the previous video, and we showed that it's a homomorphism. So by the property we just proved, we also know that the inverse function, which takes elements of the codomain back to the elements of the domain that they came from, is also a homomorphism. Well, you probably know what the inverse function in this case is. It's the natural logarithm of x. So to say that the inverse function is a homomorphism, remembering that the group operation on the left is multiplication and the group operation on the right is addition, is the same as saying for any positive real numbers x and y, when you take the logarithm of x times y, you get the same thing as log x plus log y. So this is just the property of logarithms that corresponds to the additive property of exponentials that we used back when we were showing this map as a homomorphism. Okay, well that's the end of this video. Thanks for watching. In the next video, we're going to use the properties that we just proved to give a simple proof of a classical theorem called Cayley's theorem.